cut by x. And this is the codine dimension. So it lives in the state, it's either minus infinity, 0, 1, up to dimension x. Yeah. So the codine dimension in condition 3 assume it to be non-negative. So that's the codine dimension. So anyway, there's a jump here, I guess, because this, you can see the reason. We don't use minus 1, use minus infinity. I guess you can understand. Now the example, like here, if my x is given by degree d polynomial, then you can show that the codine dimension of x, x is given here. You can calculate this one. It's either positive equals 0 or negative. So this is the case when the degree d is larger than equal to n plus 2. This is when d equal to n plus 1. So d less than equal n. So you can see that most of the case, the codine dimension is positive. Yeah, okay. So I guess I explained everything in the right. Okay. Yeah, so even the canonical divisor I explained. All right, okay. Yeah, okay. Now next, so you see that in the early case, we consider the case where the canonical divisor is kind of effective, right? So next case where is the case where the canonical divisor is not pseudo effective, or the codine dimension is negative. So now the key case in the case where the codine dimension is negative is when instead of kx to be effective, you have this, the negative k is kind of effective, or even it's ample, it's like a hyperplane. So this is the key case in the case where canonical divisor is not effective. So you assume the negative k is ample, it's like a hyperplane here. Yeah. So this is the definition. We call such an x with minus k ample final variety. You can see that this is the case where your x is final variety. So here. Okay. So in the hyperplane case, if the degree is smaller, then it's a final variety. Yeah, so that's the definition. Then the minimum model program, the short form is MMP. The other notion is called Morris program. So it says that you start with X project variety and singularity not so bad. It's called Kawamata log terminal as mentioned in the previous theorem. And then you can run this MMP assuming that the canonical divisor is not pseudo effective, is not effective. So it's kind of opposite. It's kind of minus k is effective, but yeah. So anyway, so canonical divisor is not a limit effective divisor. Then you can run MMP. So this part is a birational contraction. So these varieties all have the same dimension. So these are so-called birational. So you can have a divisorial contraction. In that case, it's a morphism. So you have solid arrow. Or you may have a flip, and then it will be pseudo-automorphism or isomorphism in codimension 1. Away from codimension 2, it's isomorphism. So this part, so there are two types. So that's the birational part. Then the dimension will be preserved. And the assumption that canonical divisor is not pseudo-effective, and this condition will be preserved by this operation. Then the paper by BCHM saying that you can go this birational operation, and you cannot go forever because the Picard number either drop or preserved. So there's certain flip, the termination flip is not known in general, but in this under this assumption, you can say that flip cannot continue forever. So you eventually you have the drop dimension, so you have to have a final contraction. So up to here, these are birational, they have the same dimension, but eventually you have the drop dimension, you have final contraction, meaning that a general fiber over a point here, you have the pre-image point downstairs, you get a fiber. The fiber will be phantom variety. You have phantom contraction. Then you can work on this downstairs, so you can continue this MMP. Then you can do the bilateral contraction and phantom and so on. But dimension cannot continue forever. Eventually, you will go down. And so long you have this condition, cannot divide, not pseudo-effective, you can continue forever. But the dimension cannot drop forever, so that's why you have to stop, meaning that the canonical divisor Y must be pseudo-effective. But once Y has canonical divisor pseudo-effective, we can use the early theorem is saying that if canonical divisor pseudo-effective, then Y is a Q abelian, is covered by abelian variety. So the structure Y is very, very precise. So anyway, let's revise. It say that you start with X, you run MMP bidirectionally, you go final contraction and so on. Eventually, you go to case where canonical divisor pseudo-effective, right? And so the final one will be Q abelian, and the middle one, the fibers are phantom variety. So the building block very clear, phantom variety and Q abelian. So that's the example I mentioned. I have two type of example. This is the abelian variety. The other is kind of phantom case. Yeah. So far you see you don't have the symmetry. We have just the pure mini model program. Now here we have symmetry now. So we have an endomorphism F. It's surjective. We assume it's interamplified. You just assume it's endomorphic, that it's too weak. So we assume it's interamplified. But in number theory, people assume it's polarized. That's more than enough. So they say that you can descend this endomorphism to the next object. Remember in the MMP, you start with X, you do a contraction to next one, X2, and so on. So you can descend the endomorphic F to somewhere downstairs. In general, after descending, the map here is only a rational map or melomorphic map, may not be a regular map. So the assumption here that my F is interamplified, and this assumption you can descend to the endomorphic to the next object, but still it's regular. But you have to iterate this endomorphism a few times so that to make it regular. Okay, so in that sense, you can descend the F endomorphism to the next object. In that sense, we say that this is equivalent relative to the actual endomorphism. So anyway, you can do this descending of endomorphism. Eventually, you can descend to the Y, and then it's still also in regular endomorphism. And this Y will be we know that the last one will be Q abelian. So that's the so-called equivalent minimum model program. So the pure case is just MMP, and here we have a symmetry. Now, actually, we can do better in the sense that you not just descend this F to downstairs to Xi to Y. Actually, you descend the whole monoid of all the endomorphism, the whole monoid as a regular action on each subject. But you cannot do the whole thing. Actually, you have to take a final index sub semigroup. So the whole semigroup may not be descending, but you can take a final index sub monoid, and then you can descend. Precisely, you have the next theorem. So this is the result. It's saying that you start with the endomorphism, assume it's interamplified. You can assume it's like a polarized case. These are the examples. Right. Yeah. And then you can run MMP. You say that it's equivalent relative to this the whole monoid, but you have to replace this one by a final index submonoid. So this one almost act on each object regularly. Yeah, that's the thing. And eventually the final one will be Q abelian. Okay, so we can run a mini model program equivalently. And then so the final one is Q abelian, as I mentioned. And there's a remark is saying that if you start with X smooth, you assume it's a rational connect. Rational connect means you take any 2 points in X, it's connected by rational curve. In this case, you can see that you can run the MMP, eventually you can reach a point. So in general, you have to stop somewhere at Y, but actually you can reach a point. So the MMP can go down to a point. So each fiber in the MMP is a phantom variety. in that sense, in this case, in this remark case, so you are reducing to the phantom case. So every fiber phantom variety, I mean general fiber. Okay, so basically, to consider symmetry, you look at phantom variety. That's enough. So that's our purpose to reduce the dimension. Now the rational connector is a concept in I guess in algeometry, also in the study of algebra. So you take X to be a variety, is called a rational connect. If you take any 2 points, it's connected by a rational curve. So the rational curve might be singular, but it's dominated by P1. So in that sense, it's called rational connect. Now the examples are very easy. Okay, so in general, you have this so-called unirational implied rational connect, and then you have reduction rational and stable rational and so on. So I'm not going to mention. Okay, so then you have rational variety, meaning that it's birational, away from coordination, away from closed subset. It's like a Pn. So in general, we can consider rational variety, meaning that it's like a Pn, up to blue down. And then this one implies unirational, meaning that it's dominated by rational variety. Unirational implies rational connect. Okay. The converse is not true. This is an open question. It's not known in dimension 3 or high. So if you are looking for a project, you can work on this one, but it's very hard. So this is okay if dimension less than or equal 2. In dimension 1, it's Liu-Law's theorem is true. In dimension 2, you can use Castellan-Volva's theorem. You can say it's true. But in dimension 3 or high, it's open. It's very hard. Okay. If we can solve this one, surely it will be more than Ando's paper. Okay. All right. So that's the definition. Then okay. Yeah. Now the key step in the proof is, we want to make the minimal program equivalent, meaning that you want to descend the endomorphism action to somewhere downstairs. So the key is this theorem here. Before that, let me introduce a definition. So the X project variety, then you take a curve C, and then you have a corresponding this class. So this is meaning that you can regard this one as in the cohomology class, or or in the curve class module numerical equivalence. So we say that this C is contractible. Geometry meaning that you have a morphism, you take a C to a point. So that's so-called contractible. But algebraically, we define this one. You say that C is contractible if you have morphism from X to the Y with the condition here. The first condition more or less is saying that the fibers of this morphism is connect, right? So and then the second condition is saying that you can contract a curve to a point. That's the case if and only if the class of C prime is a multiple of C, right? So this means the multiple of C. So C is contractible, and if the class of C prime is a multiple C, then it's also contractible. So if numerically C prime is a multiple of C as a cohomology class, then it's contractible. And the converse is also true. It's if and only if. The other thing that if your D has intersection with C to be 0, it's true if and only if D is a pullback from downstairs. In general, if you have divided downstairs, you pull back to upstairs, then you see that this pullback has 0 intersection with fiber because it's coming from downstairs. You can avoid the fiber. So it's just saying that actually the converse is true if it's pullback, then the intersection with C0 and the converse are true. So if you have these three conditions, then we say that C is contractible. So C is a curve. So yeah. Now there's one sufficient condition. If X has a singularity, it's log canonical, and you also assume it's K negative. So the intersection with the canonical divisor is negative. This condition is automatical if it's a phantom variety. In the case of phantom variety, minus K is positive, so C dot Kx always negative. It's automatic. So under this assumption, if X smooth, fine, even if it has singularity, it's all right. Then so long as C is K negative, then you always have such a contraction. These are the contractions appearing in mini model program. With this C, we have this pi. The theorem is saying that this kind of contractible class C, you only have finite many under the assumption that my F is if I have an endomorphism which is inter-amplified. So you only have finite many such a contractible curves. You don't care whether it's K negative or not. So hence, if you iterate this endomorphic F, then your F will permute these contractible classes. So if you iterate F, then F will fix every such a contractible curve. Then you can apply the MMP. The minimum model program is kind of determined by the contractible ray. Is determined by contractible curve. So if your curve is fixed by F, then the MMP will be equivalent automatically. Yeah. So that's the the theorem. So let me mention a bit the meaning of the contractible curve. So you start with X equal X1, you do the contraction, meaning that this is pi. So this pi is kind of determined by the curve class C. So you have F acting here. So if we can show that F low star C, the push forward is numerically equal to C, then you can have an inducer map endomorphism here. Let's see. So because the contraction is determined by this C, so if your C is fixed as a class, then you can descend this endomorphism to downstairs. So that's the equivalence. Okay. I still have 20 minutes, right? Okay, I suppose to finish 10 minutes earlier. Okay, I know. Okay. So now so let's summarize the most important results we have. So you assume you have an endomorphism, it's polarized or inter-amplified, and then first you can get something geometric. So the minus K is effective. So yeah, that's the thing. The other thing that you can run MMP equivalently, you can reach your final Q abelian variety. That one I mentioned already. So any questions so far? Okay. Now in the case of dimension 2, you can require less conditions. That is, just take a F endomorphism degree at this 2. So we don't consider automorphism case. Automorphism actually is more random. You take a P2 below about 10 points, as in the case of Nagata, you have infinite many minus 1 curve. Then usually the automorphism permute these infinite many minus 1 curve. So if we want to blow down a minus 1 curve, then you cannot do it equivalent because the endomorphism is just permuting them, right? Okay. So in that sense, we assume degree at 2. That's more natural. So we don't assume it's inter-amplified or polarized. Okay. So we just assume degree at 2. Then first, the singularity not so bad. It's log canonic. Actually, I can give a definition of log canonic. So algebraic geometry is not really hard. So we can. So my X project variety, I take a resolution by Hironaga, say assume so it's smooth. I introduced a canonic divisor already. So you have this relative canonic divisor. So the canonic divisor here minus the pullback of the one downstairs. And this the difference is the accepted divisor. So the sum of AI, EI. So the EIs are contract to lower dimensional. So this is divisor, so contract to low dimension. So so KLT is short form Kawamoto log terminal if and only if AIs are at least larger than -1. So log canonical if and only if AIs are larger than equal to -1. Okay, it's very simple. Yeah. So that's the definition of KLT. I mentioned briefly. Here the LC case. Okay. So Jonathan Wall in the 90s, at that time, ALC, the concept not introduced. So he has a proof, but it's not called ALC anyway. ALC, maybe there, yeah, okay, anyway. And then the mini-model program is equivalent in that case. So first by Nakayama, and in the smooth case, then we extend to the singular case. The other case, canonical divisor is pseudo effect. That's the easy case. You can see that X is covered by a billion variety or the elliptical cross high genus. The non-pseudo effect case is the essential case. In that case, you can show that F is either polarized or it's so-called delta imprimitive, meaning that you have a fibration from X to Y. Where the dynamic degree is preserved. So you have f x to x, then you have descent to something y. And the dynamic degree of x is equal to dynamic degree I'm going to introduce on y. Okay. So in that sense, the complexity is preserved, so you can reduce the low dimension. So here dimension 2 and there dimension 1 is a curve. Okay. So that's so-called delta imprimitive. Delta is short form for the dynamic degree. So that's next. So here the definition. There are two different ways to define. For algebra geometry, you take an ample divisor or you take a NEF. I use a NEF, right, big, and then you take a pullback and then intersection with the next one. Then this will be a number. And then take m's root and take a limit, and the limit exists is called this one the dynamic degree. So it depends only on your endomorphic f. The other one is more linear algebra. Look at the Naylor-Savelli group. The Naylor-Savelli group is equal to divisors modulo numerical equivalence. Yeah. You can embed this one in a smooth case H11. So we assume some basic knowledge of Kähler geometries. So so this is a linear space. Usually we define over R, so R coefficient, yeah. So R vector space, finite dimensional. H11 is also you can consider over R. So just look at the linear action of this endomorphism on this linear space. Then look at the eigenvalue. Look at the modulus. The maximum one is called the spectral radius. Actually, I didn't know this notion 10 years ago. So I guess in linear book, we have this notion? Yeah, I didn't know this 10 years ago, really. Yeah. When I was student, in Shanghai, I didn't learn this one, sorry. And so that's called the spectral radius. And actually, this one is equal to that one. These two are same. Now the dynamic degree actually preserved by a generic finite map. So if x and y it's a dominant map, they have the same dimension, and the action equivalent, the f and on x and the g on y are compatible, then these two dynamic degree actually same. So if the difference of x and y is a generic finite map, then the complexity is the same. Okay, so. Then a bunch of definition is imprimitive, meaning that you can descend the endomorphism to downstairs, dimension smaller. Primitive means it's not descendable. Data implementing means you can do descending, and further the dynamic degree preserved. Data primitive means it's not the case. Then you have strongly implementing, meaning that you can do descending to low dimension one. Actually, the action on downstairs is almost trivial after iteration. So basically, you are acting on the genetic fiber, so it's still low dimension. You can do reduction. Weakly primitive means that you may descend, but you cannot have an action trivial on the base even after iteration. So this is so-called dream BBC. It says that if you have a endomorphism, which is not an automorphism, and then up to taking final cover, then we claim that it's either data imprimitive, you can reduce the low dimension, or strongly imprimitive, meaning that you can reduce the genetic fiber, still low dimension. Or quasi-abelian is the known case. I guess we mentioned somewhere here. And then you also have polarized. So we also had a polarized case. So a polarized case is well studied in number theory. So for geometry, I guess we just stop here. So leave the the study to the number theory people. Now, so I guess I will mention two theorem and two applications. So the theorem A is that the minimal model program, the bidirection case is equivalent. The assumption is that F is not automorphism, and it's data primitive, and it's smooth and dimension 3. So data primitive is natural because otherwise you can reduce to low dimension case. Smooth is some condition I need, and also dimension 3. Okay, that's the theorem. So next example is saying that being data primitive is needed. Otherwise, we have counterexample. Yeah. Now this is the theorem. The second theorem, as I said, I only have two theorems and two applications. So so again, I take an endomorphism, which is not an automorphism, and it's a dimension 3 case, and it's smooth. So the codal dimension, you can see that you have three possibilities: codal dimension negative, 0, or positive. The first case, the main case, is saying that if codal dimension negative, then it's either delta imprimitive, so we can reduce the low dimension case, or strongly imprimitive, we can reduce the genetic fiber case, still low dimension, or it's polarized. And polarized is it's kind of well understood case, or well studied case. The next case is kappa equals 0, codal dimension 0. Then you take a quasi-eta, I guess take a eta cover become my X smooth. Then the cover will be either abelian variety, or it's a little bit curved cross K3 surface. Then you can reduce to the abelian variety case, or reduce to the product case of low dimension. So it's kind of done. And the final case is kind of easy. So if codal dimension positive, then you can have an E-dagger fibration, then you can descend the X to the base of E-dagger fibration, and the action on the base will be automorphism of final order. So let me briefly mention this final case. It's very useful, but I'm not sure whether it's well known or not. Okay. So what we do is that given X, you can have an E-dagger fibration. Y, it's not usually it's a rational map. So you remember that you have H0 of X, MKX. So take U of this one. You take a section S0 to Sn. Then what you do that you take X to the evaluation of this section. Oh, that's the it's called phi of MKX. I'm using the notation of GTM or E-dagger. And that's the E-dagger fibration. And so this is the image of Y. So dimension Y is equal to kappa of X codal dimension. So that's another definition of codal dimension. So actually once E-dagger told me that he got an award, he's supposed to introduce his study to the emperor. 1 minute. So he said he was able to introduce to the emperor what he studied in 1 minute. So actually, many things actually you can give it a very short way. So I was a student in Osaka, so he gave a lecture there. And then, so this is the collaboration. So so if you have an endomorphism here, you can have an induced map on Y. So so the claim that although your f on x is degree at least 2 or so, but the action on Y will be automorphism and final order. So initially it was proved by Nakamura and Ueno, but assuming Y is non-unilutal, and then Deligny removed that condition. And then with Nakayama, I guess we extended to the case where X is a Kähler manifold and this F is a melomorphic map dominant. You can get the same result. Any dimension. If in the morphism, sorry. If you can in the case of abelian variety, you can regard as matrix. Yeah, you have a lifting to the Cn. Yeah, correct. It's a matrix. Otherwise, it's just is a morphism. Yeah, okay, it's like a topology map. Yeah, correct. The variety defined over Q bar. So now it's number theory. So I take ample divisor. You have the corresponding wave height. Then evaluate this wave height at the iteration of x. I take a maximum, and then take absolute, take a limit. That's so-called the arithmetic degree of f at a point x. Now the conjecture by Kawaguchi and Seelman in 2016 is saying that these two quantities should be same. And the right-hand side, the dynamic degree are introduced. So this is a global invariant. It does not depend on your point. It depends only on f and the the endomorphism. And the left-hand side depends on your x. But these two are supposed to be equal. The assumption on x is that the orbital x and the action f is the risk dense. Okay, so so in general, it's known that the left-hand side is less than equal to the right-hand side. So the claim that it's equality. So let's move on. So it's let's some remark. So the known results is that if it's quasi-abelian, we see the abelian case is known. The polarized case is also known. That's why I say that polarized is well understood. Strongly primitive is vacuous known. Hyperkähler, you have this quadratic form. It's like a surface case. It's known. And dimension 2 or so that it's known. So in the smooth case by Matsuzawa, Sano, and Shibata, so we extended to singular case. Yeah. Then so in dimension 3 high is still unknown. And some progress if the irregularity is positive and so on, it's proved. So irregularity means that it's half of the first Betti number. So if B1 is positive, Q is just half of Betti number, first Betti number. Then. So the application of our theorem is that this Kawaguchi-Seelman conjecture is true for any endomorphism which is not automorphism. I mean degree at least 2, if the variety dimension 3 is smooth. Now the smoothness is used because in the minimum model program you try to keep in the smooth category, but at one point, you may go to some singular one. You go to singular because there's a reason you have to contract a surface, a divisor. So we need to use that divisor to look at the actual endomorphism on this divisor. Divisor produce singular point if we contract it. So you utilize that divisor to do some dynamic process. So that's the reason we need a smooth. So there's one more conjecture. As I said, I have 2 applications. I had one, it's called the least dense object conjecture. That one is even harder. Again, it's endomorphism. It says that there are only 2 possibilities. Either the pullback action on the function field has a non-trivial invariant function, or it has a dense orbit. So it's called Series dense orbit conjecture. So either you have a non-constant function, so it induces a natural map to P1. So in the first case, you have a X to a P1, you have a rational map, it's fixed by F. So you have invariant vibration, so you cannot have dense orbit because you have vibration is fixed, and each fiber is fixed, so you cannot have dense orbit. Or you have it must be dense orbit, right? And this is unknown in general. So in domain 2, it's very recent. It's 2022 by Junyi Xie. He's in Beijing now. Yeah, so it's proved in a smooth case that Junyi and my former student Jia PhD, we extended the singular case. So in domain 2, it's proved. Domain 3 is still open. The thing that it's harder, even look at P1 cross P1, you look at the projection. The thing that if you have vibration, you know the conjecture true for the fiber and for the base, you still cannot prove it, right? So yeah, that's the harder case. So the application here is that in domain 3, we want to say that it's a resistance object conjecture true. So suppose it's not, then you say that it must be unit-load. So you can run a mini-model program, and the mini-model program is equivalent. So we remember that the dynamic degree and so on are preserved by bidirectional map. So you can run MMP, keeping the same endomorphism action. And eventually, dimension cannot be preserved forever. You can have final contraction, and this is the equivalent. You have action F on this variety and also on Y, and this final contraction. So Y has lower dimension. So basically, we reduce this ZDU to the final contract case. So I guess this I don't have minutes. So this is the one key idea. Is a new notion introduced in our paper. So take a divisor, coordination 1. You take a pullback, then look at the vector space, subspace spanned by these. This is the Picard group. So it's generated by Cartier divisor, so it's infinite dimensional. But however, the subspace here generated by them is finite dimensional. So you can have a pullback F on the finite dimensional case. It's a linear algebra. Then you look at the Z prime in the vector space. You look at the codine dimension. I mean, just like a codine dimension definition, we have similar definition. Yeah, you can look at here. Instead of K, I consider D. I just consider D. Okay, then the image, its dimension is the E D dimension. So these are the E D dimension. You take a maximum, then you have a corresponding map, just like here. And then in general, the endomorphism F on X does not descend as a regular action on downstairs. But if we take a choice reduction, you choose some the codomain nicely. I mean, not nice. I mean, actually, there's only one choice. You choose a choice reduction. This Y, then you can descend the F on X to Y. Then you can work on this so-called dynamic E-dagger vibration. So that's the main notion. I don't have time, so okay. So let me. How come? Also running out of battery, I see, with no more battery. So let me stop here.
谢。